Hey everybody, it's Tom Cheriams with the FujiNet project, and I wanted to make a video, a rather in-depth video, showing a walkthrough how the Atom side of the firmware works, particularly how the ESP32 side of the firmware works, and how that relates to the Atom side of the code, so that you guys can understand a bit better about how FujiNet actually works. I wanted to apologize ahead of time. My voice is a bit cracked because I'm a little bit under the weather, but we will all try to weather through this as best we can. To start, let's go ahead and do a demonstration of the test program that we're going to be using to demonstrate the test network device that I'm going to show you throughout the rest of this video. I have a file server here running on my local network, which is basically where I put files as I'm developing them and working through them, so that I can take and compile things and quickly test them when they're ready. So for this, we'll go ahead and go here to the text40 version of Simpleterm. We'll go ahead and mount it read-only, and then we'll boot it. Oop, actually, let's try that one more time. This is a very, very simple program, and it uses the 64-column ANSI console. We'll connect to bbs.fostex.net on port 23. As we can see here, it's working just fine. We're able to connect to this remote telnet site and use it from the Coleco Atom through the FujiNet. So the FujiNet is providing a TCP connection directly to bbs.fostex.net, translating it, and sending the result through AdamNet back to the Atom in a form that it can understand. We won't really do anything here. We'll just log off. Apologies. So there we go. I mean, here it is. You can see it works. We'll go ahead and put this to the side for a minute, and we'll look at the code which comprises the Atom side of this in just a moment. But first, I wanted to take you through a bit of the firmware that shows how the ESP32 side of this actually works. For those of you that want to follow along, of course, you can go download the firmware from GitHub at this address. Pull it down and install VS Code and Platform IO, and you will have everything that you need to build this firmware and deploy it onto an ESP32 device for FujiNet development, even before the boards are finished. For a bit more information, we can go to the FujiNet Platform IO wiki, and there's a section on board bringup. Showing you how to take and set up the development environment, get all the pieces that you need to get installed, any fixes that need to happen along the way, how to clone the FujiNet repository, and get everything running so that you can upload the result to your board. Once you have everything set up, you can go into VS Code and open up the project and look at all of the individual bits and pieces of the FujiNet code. There's a lot of it. not just because we have multiple bus types, but because we are supporting multiple peripherals at the same time on the same ESP32. We've tried to separate everything up as much as we possibly can into different concerns for the different subsystems, such as the low-level hardware, media types supported by different systems, the different sub-devices like the modem, the printer emulator, CP/M emulation for platforms that support it, SAM for speech synthesis, TCP/IP routines, and the like. But there are also the individual device interfaces for each of the peripheral types. You'll see here that we have the devices for AdamNet, for IEC for Commodore-based machines, and for SIO devices for Atari 8-bit systems currently. More will be added, such as SmartPort for Apple II. But to start, let's take a little look through main.cpp, where everything essentially starts up. Inside source, we find main CPP, and we find all the bits and pieces that we need to include. Let's go all the way down to main. We start by basically setting up the basic hardware and creating our primary task, which for right now is a high priority task pinned to the main CPU. Once that's done, this thread here just sits and idles. This is the function that's called to start the new thread, and the program essentially sits here and cycles through the service function for the given bus. If we go into it a little bit more, we process anything that we've queued up to process later, which currently isn't anything, but I'm going to take and move some of the long-running network operations into this function later. And if we have anything that's waiting on our serial I/O UART, then we go ahead and process it. This is a function, this is an object that is copied over from Arduino. We've taken it, modified it, tweaked it a bit for use in ESP-IDF, which is the framework that we're using to write the firmware in. You can dig into it if you wish. You'll see that it has functions for reading and writing to the individual UARTs to send data in and out of a particular serial port. So we go ahead, and the first thing that we do is we set up the bus. We set it to the AdamNet baud of 62,500 bits per second. We flush anything that might be sitting there for one reason or another, just to get everything clean. And then we immediately go ahead and start processing commands that come through. If you read the Coleco Adam Technical Reference Manual that's available, you'll see in Chapter 4 a discussion about AdamNet and how the different packets are basically set up. We start by reading the first byte of anything that's incoming, which will be the type of packet along with the device it's intended for. We go ahead and separate out the device that it's intended for by masking off the bits we don't need, which in this case is the top 4 bits. This becomes the device. We go ahead and turn on the indicator LED to indicate that we're going to service something. And then we basically iterate through what is essentially a map of the individual devices, match it to the device ID, and if we find it, if we don't find it, then this packet isn't meant for any of our devices, and we wait for the next one. Looking at wait for idle, this is a very important function to make sure that we only transmit when we can, and we ignore anything that's not meant for us. Since we don't really have hardware support to tell us whenever the bus is quiet, we try to derive that by listening to the serial bus. And if there's data, we read it and drain it out. Then we start a timer, and we basically count the amount of time since we last heard from something. And if it's long enough, in this case 150 microseconds, then we indicate that the bus is now idle, and we exit the function. If something comes in before this time, the whole sequence is restarted. If we go back and look through now, if we do have something that does match, then we go into the daisy chain and pass into its AdamNet process loop. Now, if we look at daisy chain as to what daisy chain actually is, it's a map of AdamNet devices that are referenced by their device ID number. And you can dig into this further. So if we take a look, we can see, for example, in AdamNet.h, that we have some helper functions here, but we have an AdamNet device, which gives us a couple of functions to help us send and receive data. Arguably, these could be moved to the bus, and they probably should. And we have some helper functions for not only receiving and sending single bytes, but for grouping buffers of bytes together, sending and receiving them, as well as a couple of convenience functions for quickly getting the 16-bit length identifiers that commonly comprise different AdamNet packets. We also have a fetch shutdown method. And finally, each AdamNet device has an AdamNet process, which as part of that process, it's given the first byte of that packet. Since we've already determined by the time we get here that this packet is for this device, we can hand this device this first packet, and it can determine what to do with that given packet. We also have a bus class here, which holds our state for the different things like our daisy chain, the current active device, as well as a number of convenience pointers to the different types of devices, should we wish to quickly reference them from other parts of the code. We have methods for adding and removing devices from the bus, changing those device IDs. And finally, as a convenience, we have a singleton object called AdamNet, which references the bus that we are connected to. Mostly, and this is mostly used so that we can directly use wait for idle, because wait for idle is actually implemented here. So all the different AdamNet devices essentially use the functions inside of here to implement their AdamNet devices. To take a look at some of them, so that was in the bus directory. If we look in device, we'll see AdamNet devices for all sorts of things. Disk storage devices. This is the AdamNet device for device 15, which is the FujiNet control device. There's an AdamNet device for the Wi-Fi modem, an AdamNet device for network devices, AdamNet devices for printers, and there's a secondary object which basically holds the list of possible printers here. So if we go back, let me think here for just a moment. We've seen how the main loop basically loops through listens to the UART, grabs any incoming data, determines if it needs to be passed to a particular device, and then it's passed off to a particular device. So that pretty much segues us into device. And for the device we're going to take a look at here, we'll take a look at the network device. This is a network prototype device. There's not much to it. This is AdamNet. It's referenced as an AdamNet device, and it's got a few things here that we need for state keeping, such as our response buffer, some bits and pieces as to whether or not the device is ready or not, and implementations of the AdamNet process and the different commands that we need to react to. We also have a status word and the different AdamNet control packets that we know we want to respond to. We start, since we got handed off AdamNet process here, we got handed off to this function here. Now, how does it know that this is for this particular network device? Again, we have a device ID. And if we look in the, currently this is set up in the Fuji device inside of setup, we'll see that we have disk devices and different things set up here with different device IDs, 4, 5, 6, 7, etc. And we finally see one here for the network device, which we've assigned to device number 14. So now it knows, now the system knows, and the bus knows, that any packets with device ID of E need to go to the network device. This is temporary, just so I could take and prototype this out and work out how this is going to work. So once we've taken and processed the packet here, we bounce all the way back into AdamNet process here with our byte. We already know that it's for us. We don't need to deal with the device part of the bits. We want to deal with the command part. So we take the byte that we're passed in, shift over so we have the top 4 bits now become the bottom 4 bits. And then we switch between them. There are different ones for different types. Status, clear to send from the Adam. Adam wants to receive something. We want to send something to, send something. And is device actually ready? And for each of these, there's a different function for each. The simplest are the status and ready functions here. Since I'm not really returning anything special here at the present, I've already preformed a complete status response with the response data status packet here, which is of type 8, going to device E, and the size of that status packet, and finally the reserved byte here, which is not used, and this is whether or not this is a character or block device. And since this is a character device, this is set to 0. And the status word right here is currently 0. It's not being used, but it could be for different things, such as connection dropped, that sort of thing. We send that off using the AdamNet send buffer convenience function. That's a part of AdamNet CPP, and if we go to definition, we'll basically see that we wind up back here, and it just writes out the buffer. Now, mainly since this is a character device, we're controlling this device by sending things to it. The Atom is sending commands to it using the send packets. And it's the job of this function right here to figure out what's being sent here, to break it apart. And since this is a send packet, it does have a length, which we go ahead and pull out. And it has a command byte, which we want to act upon. In this case, I've defined two commands for this network device, this prototype: connect to host and send to host. Receiving is handled in the complementary function, AdamNet control receive. For connect to host, this is pretty simple. I've created a very simple protocol in that the next 256 bytes after this basically comprise of the first 2 bytes are the port number from 0 to 65,535. We go ahead and remove that from the link that we're passed in. And we grab the host name. Then from that, we go ahead and get the checksum. Now, since this is a prototype, I'm not really concerning myself with calculating the checksum, but you can calculate the checksum, and based on that, we can either send an acknowledgement or we can send a non-acknowledgement if the checksum doesn't match it. In fact, we can go ahead and do that now. We'll go ahead and make a variable for that. And we can then take and calculate the checksum. Of which there's 2 bits and pieces, the buffer and the size of that buffer. And AdamNet checksum will return the checksum value. Then we can take and acknowledge it. If we don't, then we can simply choose not to. And the other thing we would do is basically take this particular chunk of code right here and move it into here. Now you'll notice that as part of the process here, I am literally acknowledging the packet as quickly as I possibly can. And that's because, especially with the case of the network connection here, different things can happen. It might take longer than 150 microseconds or 500 microseconds even to initiate the connection. And by that time, the Atom may have already timed out. So it makes sense to try and validate the data that's sent to us and tell the Atom as quickly as possible that the data is okay, and then we can act upon it. So that's essentially the implementation of the connection command. We have connect. The Atom does a send packet. where the first byte is FF, the next 2 bytes are the port number, and the remainder of the packet is the host name. Grab it, pull it in, make sure it's okay, acknowledge it if it is, then go ahead and do the connection. Now, there are other things we could do here. You could argue that if the connection fails for one reason or another, you could simply say, you could either take and pass a non-acknowledgement if the connection failed, or you could alter the status word to indicate that the connection failed. It's all pretty much up in the air as far as anything's concerned. And I'm still kind of thinking through how to do that. The other send command is essentially send the packet of information out the socket, such as typing in characters from the keyboard. I'll go ahead and remove that. And all this is here, same basic thing. We remove the command byte because we don't need it. We receive the buffer, we receive the checksum, we wait for idle, acknowledge that we got it, and then write the result out the socket. Now you'll see client is what's called Fmtcp Client. And if you dig into it, you'll see that it's basically just a simple TCP object so that you can connect to TCP sockets and manipulate them. On the other side of things, you have what's basically the receive function. Anything that when the Atom says, I want to see if there's anything that's coming down the pipe that I should be paying attention to, it will send a receive command. At which point, we take it, and if there is nothing available whatsoever, we wait for the idle, and we send a non-acknowledgement. I copied this behavior from the keyboard controller. Seems to work rather well. We also have, if we have a response that's been pulled in that we need to deal with, we wait for idle and say, yes, there is data waiting, acknowledge it. Otherwise, if the response buffer is empty and there is data available, we go ahead, wait for idle, do a non-acknowledgement saying we can't send it right now because we still have to get it. Then we do figure out the response length from client available. Now, since the response buffer is 1024 bytes, this particular conditional ensures that the data is never more than 1024 bytes, that we never indicate that we have more than 1024 bytes available. We read in the data into the response buffer based on the calculated response length and go on. So once that's done and we send that back to the Atom will go, hey, that's great. I'm ready to receive the information. You're clear to send it to me. At which point, we can send a response back. And that response, we send a length, which is, okay, this is how many bytes we're sending back. And then we send the entirety of that buffer. Then we send the checksum of that buffer. And since we've sent that data and it's okay, we clear it out. Response length is 0. And again, you could, for example, take and check to see if an acknowledgement happens And if the acknowledgement happens, then you take and clear out the response. The only other packet that we are dealing with here is that periodically the Atom will ask a particular device if it's ready to be dealt with or not. And in this case, we simply say, yes, we're ready, and just deal with this as we need to. If the device is not ready for one reason or another, then the acknowledgement doesn't get sent, and the Atom will simply ask again until it is acknowledged. So that's really the guts of the network socket device. From the firmware side of things, you have these particular helper functions to take and define all these different devices that you can use, and your job in device is to take and build something that talks the particular bus protocol in order for the computer to communicate with that device. For the AdamNet, AdamNet. For the Atari, that's SIO. For the Commodore 64, that's IEC, and so on. Apple II, smart part. So with that, we'll actually bounce over to the PC side of things. Oh, and I will show you, as part of the process, I actually have a logic analyzer connected up that allows me. I have a tap connected to the AdamNet, which is connected to my FujiNet as well as to my computer here. And we can see the individual bytes that come across the AdamNet, how they're made up, all the way down to the binary digits if need be, as well as for start and stop bits, so we can see if there are any framing errors. In this case, this is a keyboard status command. The keyboard doesn't have anything to send, so it sends C1, which is non-acknowledgement from device 1. Okay, fine. It waits on. 41C1, 41C1. And at this particular point in time, this is actually waiting for keyboard input for me to hit the return key, because I had already entered the host name over on the other side here before I actually started the trace. You'll see that this is the return key right here, the 0D, which is the carriage return. There was something to be sent. Yes, there is something to be sent. Okay, great, send it over. The keyboard sends over the keystroke. The Atom responds with an acknowledgement. At which point, we see the first command for the network device actually taking shape here. The first thing that happens is the Atom asks if device E is ready, which is our network device. This is followed by the acknowledgement. Of course we are. And since we're answering this within the amount of time that the Atom is waiting for it, the Atom is okay with this and proceeds onward. If we took too long, the Atom either will try the command again, or it might give up after a certain period of time. 182 microseconds in this case. So we see our send command for 6E. It's 0301 bytes in hex, and it's our FF command, which is our connect command. Our port number, followed by the host name that we're going to connect to, and the rest are zeros. The Atom receives it. The FujiNet receives it. The FujiNet acknowledges that it's okay, and we continue onward. At which point, now we're actively listening for data. Is there something for me? Is there something for me? No, there's nothing for me. But there's some data for me right now. And here we go. The first bits of network data. Okay, send it in. Yes, Atom's ready to receive. we send the response. There's the BE from our code. The entirety of our network packet, right there, 1024 bytes of it. The Atom is okay with it, so it sends an acknowledgement. And this repeats over and over and over again as the data is sent through. And since this data is being displayed immediately upon receipt, there's no scanning of the keyboard or anything else that's happening during this time. And if we actually do a little bit of a time, just see how much time has passed, we can see that this is happening at around 3,000 milliseconds, which is roughly 3 seconds. It's taking 3 seconds to get that 1024 bytes worth of data and display it. During this particular point of time, the Atom is displaying the data. Nothing is happening. And then it happens again. It goes ahead and scans the keyboard just because it takes and scans the network's not ready. Oh, but there's data this time. And the process repeats. And so on. So that's a look at the data from the network side of things. We'll finish this up by looking at the code that makes up the Atom side. And for that, we'll go into our little bit of simple term, and I will use my Emacs text editor to do this. Simple term is a program that I wrote in C, compiled with Z88DK, to test the network device. It's the simplest little network device I could think of. So you'll see, remember, that our connection command is basically made up of the command, which is FF. It's the 2 bytes that have the port, the 256 bytes, which make up the host name, and that gets wrapped up into a nice and neat little structure, which will allow me to use, to build this quite easily and just send it out. We have a little banner, which just basically, yes, okay, this is the banner you see at the beginning. You see the connect, where you get the host name and the port, and we attempt the connection. Set the host command, the connect command, set everything up, and since we're dealing with the data structures directly, we're going ahead and filling them in up here. And then we use the EOS write character device function to take and write this command out to the AdamNet through EOS. This particular function is actually part of EOSLib. And if we take a look, we can actually dig into it here. Apologies. And we'll see that there is a library here on GitHub of EOS functions that I've wrapped in C. And all these do is call the appropriate function inside the EOS ROM. And every single EOS function that I could find, I made a wrapper for it. Every one. So the one that we're looking at here, EOS write character device. And this is a wrapper for start write character device and end write character device, which, if we dig into it a bit, we'll see that it basically, hold on, let me just take and zoom in a little bit. If I can find the zoom button, there we go. It basically starts the write and spins on the write until something is finished, until something happens, until the command completes. If the upper nibble for one reason or another is a 9, then we probably timed out and we should try to do it again. Otherwise, we take and return the result of the status. So we can figure out, for example, if the command was successful or if there was a non-acknowledgement, for example. Breaking this down a bit further, we'll see start write character device. And many of the functions inside of EOSLib follow this same pattern. We set up the individual individual Z80 processor registers, and then we do an assembler call to the appropriate function inside of EOS. And when this happens, the registers get updated, and we return the important ones that we want to return. There we go. So with that, that's how all of the different EOS functions in here actually work. So we're using an EOS function here to take and send to write to the character device. This turns into a send packet, which gets sent across the bus, and the FujiNet grabs it and interprets it, does the connection. And at that particular point, you'll see that we do the banner, the connect, and then we jump into the terminal program. And the terminal program starts by starting the keyboard read, priming it as we need it, and then basically looping through in and out. In is used for reading the keyboard and sending anything out. And if we need to send something out, we construct a send packet, which is FE, which you saw in the firmware earlier, with the 1 byte that we want to send out, setting it appropriately, and forming the EOS write character device call to do it. We then immediately start the process of reading the keyboard again. And out, simple enough here. All we're basically doing at this point is we're reading character device, and if we get an 80, which is an acknowledgement, everything okay, then it means that there's data waiting for us. And so we go ahead and we grab how many bytes are waiting. We know this because we have the device command block here. And we iterate through it, outputting it to the screen. Now, where is DCB coming from? We'll see that we have EOSLib has in EOS.h a structure for describing a device command block. A device command block basically is the elementary, you can think of it as the atom for all things AdamNet, the atom of all things AdamNet. It's a section of memory that basically the I/O processors, the 6801s, read and write to as input and output is performed on the AdamNet. And it has a whole bunch of different bytes here that have different uses, such as the status of the last command, the destination buffer or source buffer that an I/O operation needs to use, and the number of bytes that need to be dealt with in the particular transaction, as well as the maximum number of bytes which can be dealt with in a particular transaction. And in this case, what we're doing, when the program starts up, we use the EOS find DCB function that's part of EOS and say net, we want to find device E. And if we find it, it gets put into the DCB pointer here variable that's referenced to here. And from that point, we can reference any of these individual bits of the structure to get useful information about the input and output that we've done to a particular device. In our case, we're basically using it so that we know how many bytes have come in so that we can put them to the screen. So really, in essence, this is the crux of doing FujiNet development if you want to talk to the FujiNet directly. For certain devices like the disk drives and whatnot, there are disk drivers already inside EOS. Those things just work. But for things like the network device, this is essentially what you have to do to read and write from it. And you'll notice I didn't invent anything new from the Adam side of things. I'm using the existing EOS calls to read and write from the character devices to do all the different transactions and things that you need to do to talk over the network. It's expressed in terms that already exist on the Atom, and that's one of the points of FujiNet in the first place. So with that, I think I'm going to leave this video here. I really want to get feedback from some of you as to what else I should cover here as this is being developed, in an effort not only to help promote understanding of how to program new applications and things for the FujiNet, but to get the Atom community and all of the different 8-bit communities together to work on the firmware to add new features. So, I hope you guys enjoyed this, and until next time, guys, have fun.